So one more plane ride in our journey this afternoon is going to take us across the Pacific Ocean to the great state of Hawaii, and our final speaker, Stephen Baldridge of Baldridge & Associates. Please welcome him to the podium.
Just in Hawaii, we actually, when we welcome people, we say aloha. It's one of the few states that has its own kind of a separate language, indigenous language. And very interesting, the state motto is, "The life of the land is perpetuated in righteousness." The life of the land is perpetuated in righteousness. And that goes back to Native peoples really taking a strong step to make sure they don't overfish, overharvest. Sustainable design, which was required to sustain life. The background, this is actually a photo taken close to where my house is, and I'm only 20 kilometers from downtown. I definitely want the islands to remain sustainable, but I think there is a place for high-rise construction there. Now this is the bad image of high-rise. Just a whole lot of buildings, no real thought to how they're placed or put into the environment. And there's actually a lot of people in Hawaii who have grown to hate high-rise buildings and construction and development. But at the same time, we have a problem with housing. We don't have enough housing, especially affordable housing. And the only way you're going to do affordable housing in a tight, expensive land market is to go up. So tall can be sustainable. The cities around the world, especially in Europe, they're looking at, and they have a problem with tall because of the historic nature of their cities and the communities. In Hawaii, it's losing touch with the rural feel and the great tropical place that it is. And many people in Hawaii don't want Hawaii to become a Miami or Hong Kong. But in reality, we're a major city, 1 million people out in the middle of nowhere, one of the most remote cities, actually the most remote large city in the world. Skyscraper density, I found this actually at one point, Hawaii was number 3 on this list, or Honolulu, I should say. Honolulu is on the island of Oahu. So we have a pretty high density of skyscrapers, and that goes again to land that's reserved for agriculture, land in the urban core, land is very expensive. What we've had, though, is a problem with misguided height restrictions. The building heights have been limited to 350 to 400 feet. These restrictions date back to the 50s, when growth was, they wanted to temper growth a little bit and to take advantage of the mountain and ocean views. I think Vancouver has done an excellent job of allowing buildings to go taller and actually making more view planes to the mountains and the oceans, and I hope at some point Hawaii does. Our height limit was pretty much limited to 1/2 the height of Diamond Head, which is a landmark in Honolulu. And the bottoms on the right are some of the high-rises in Honolulu. They look pretty small, dwarfed when you compare them to the Sears Tower in Taipei 101. But there's also been a side effect of height restrictions. Communities grow and change. The restrictions have actually created a lot of monotony in the landscape. And what we're ending up with, if you look at Waikiki from the ocean, you see every rooftop is at 350 feet. You can't see in between these buildings anymore. The developers, in order to make these buildings work, they have to maximize their floor areas. And when they maximize their floor areas, they're maximizing their height. Every one of these developers would have loved to have gone higher. And in doing so, they can actually make the buildings not as wide and not as fat. And from this particular angle, you can't see anything between any of these buildings. It's really quite a shame. But tall is truly sustainable, and we're really trying to get that across. It's difficult because you have a lot of people like, we want the parts of the island to remain country. And I'm like, that's great, because if we're going to have the scene like you saw on the first slide, we have to also have an urban area. So Honolulu is now starting to look at some of the mistakes that they've made and getting into maybe we should go higher. And I think this is a great quote from one of the council chairmen, is what motivates me is I think one of the reasons a lot of people choose to live in Hawaii is its beautiful natural environment. So we have a choice. Either we continue to pave over paradise and build out, or look at going up. We're getting ready to do our first transit, very expensive project. I figured if you took that same money and built buildings, taller buildings in town with that, the cost of building those buildings would actually be cheaper than the transit, and you would have more people closer to the urban core. There's also been an unexpected benefit to these height restrictions. Buildings have had to be very, very efficient. Another city that might be comparable to this is actually Washington, D.C., where height restrictions are based upon the Capitol building. We have a lot of buildings that have floor-to-floor heights of 8'6", 8'5". We have parking decks in buildings where the floor-to-floor height is only 8 feet. And there was a local architect in Honolulu, actually did quite a few number of 40-story plus buildings. They weren't the prettiest buildings, but he kind of created a little bit of a prototype. Oh, I guess that's not going to work. But anyway, this is an example of a building with only a 5-inch, 125-millimeter slab. Even the walls are only 5 inches thick. And the only reason they're doing this is because they're going to get as many floors as they possibly can within a height restriction. The one advantage of that is your buildings are a lot more efficient. So when we talk about sustainable design as structural engineers, everyone talks about fly ash. Everyone talks about recycled steel. But how are we using those products? You take a bottle of water, or water for instance, tap water, bottled water in plastic, or out in the front you see some bottled water in glass. Well, tap water is the most sustainable because it's coming through the pipe system. This is probably second sustainable because it's going through that same pipe system, they're filtering it, then they're putting it in a plastic bottle that's probably not biodegradable. They're sticking that on a truck, and they're shipping it to the same place where you can get the same water essentially out of the tap. And then the least sustainable is bottled water that might be coming from Italy or France, all the way across the ocean to Dubai. So for sustainable structural design, it's really important to remember it's about how much material you're using. One of the key things that a structural engineer can do, along with helping the architect and mechanical engineers, but internally is thinking about how much material we're using. It's pretty amazing. They say the building industry consumes 3 billion tons of raw materials annually, 40% of the total material flow in the global economy. The manufacturing process of new materials is water and energy intensive. It's one of the things they say about the manufacture of cement is one of the biggest pollutants out there. Harvesting, extracting, and mining and processing of new materials is a big drain. It's a big drain on the world, especially as the rest of the world wakes up and starts to develop as well. The life of the land is perpetuated in righteousness, so we can't overmine, we can't take all the materials out. So in view of this, what you got to do is really think about, can we use less materials, minimize the consumption and depletion of material resources, minimize the life cycle impact, and from a structural engineering standpoint, the most significant contribution that we can make to sustainable design is to optimize the structural systems and reduce the material requirements of a project. We've got to reduce the materials, reduce the amount of materials. So this is one project that we have going right now. Moana Vista, it's a tower, it's 48 levels, squeezed into 400 feet. It's actually 52 levels because the parking is at 4 foot and jumps back and forth. We have high labor costs, we have a real tight labor market right now, and cost and supply implications of shipping construction materials to the most remote city in the world. We had a project recently where half a load of the steel actually fell off the barge into the ocean, delayed the project by about 3 weeks before they got somewhere out there. And even in the design concepts, we have to think what's going to fit into a container 40 feet and try to design around that, or what can fit on a barge. This was a collaborative effort. Actually, we were kind of brainstorming with the architect, and I pulled out some old books that I had. I actually had grown up in Chicago during that period of time when the Sears Tower and the John Hancock building were being built. And like the form of the X-brace actually expressed in a concrete building, which was first built in New York and then later done 2 projects in Chicago. The architect loved it. The site benefit was very efficient. So the efficiency, the structural efficiency of the overall project, we look at a number of different factors: the shear and columns, where they're laid out and how they're laid out, the slab systems. Post-tensioning is a great way, and post-tensioning is used a lot here in the Middle East. It's a great way, efficient use of materials. Advanced analysis methods. A lot of old-time analysis is actually pretty conservative, and in its conservativeness, you waste materials. Specialty construction products, high-strength materials that MMFX steel that Kira Kopinski's office has been using is getting a lot more attention now. And appropriate design philosophy. So in taller buildings, a number of strategies can be used to provide efficiency, reducing wall thicknesses and reinforcing requirements. Some of these include coupled shear walls. By linking two more walls together, they act as one instead of two separate walls. Outrigger systems. In Hawaii, a lot of people outrigger canoe, and you'll see these canoes out there, and it keeps it from tipping. It's the same concept. If you can get an arm out there, you get the moment arm, you have a much more efficient building. Punch shear walls. Residential buildings, at least in the U.S., can be very expensive to build because the exterior cladding, there's a lot of liability issues, and what we found is sometimes it's better actually to use concrete as the exterior cladding. It's almost gotten to be the same price, and then you're getting structure and cladding in one. And then shear wall frame interaction is another way. So here's an example of a coupled shear wall. We actually, in this building, we had two-story loft apartments every 10 floors, which worked out really nice. These are two examples of buildings that are using a perimeter tube or some kind of punched concrete wall. And on the Moana Vista project, we actually had a combination of X-braces on the outside, coupled walls on the inside. One of the real big criteria with this as well was to create a zero-loss building. And when we say that, in Hawaii at least, the condo laws, what you sell as sellable areas, what they call paint to paint. So it's from inside of finish to inside of finish. And we tried to come up with a system where the concrete walls would be no thicker than drywall partition, so that the owner wasn't losing any of their sellable floor area from the maximum amount of floor area they could build. So we're using a combination of thin concrete shear walls and an architecturally expressed exterior system that efficiently resists the lateral seismic and hurricane forces. We had no uplift in our foundations because we had a big arm that we engaged in this system. Column layout is really important too, and you'll find that a lot of times the architects are laying things out and they may not be thinking about the implication. So the thickness of the structural system, of course, is dependent on where you put the columns, and the further apart you put them, of course, the thicker this slab system is going to have to be. So it's important that we get in early and work with the architect to tweak things and move things around a little bit, and just kind of massage the column layout. On the Moana Vista project, the unit layouts were about 10 meters wide. We needed to get a 6-inch slab, maximum 6-inch slab on this thing, 150 millimeters to get it to work. And we actually combined an upturned beam at the perimeter that would support the glazing along with the thin slab. So for the slab systems, from an optimization standpoint, you really can't beat post-tension. Post-tension slab is usually about 25 to 30% less thick than a normal reinforced slab. You're getting maximum efficiency because the high-strength steel cables are actually draped to follow the stresses in the slab, so there's no waste reinforcing. And the use of post-tension in a slab system represents not only a reduction in material requirements, but a reduction in the overall weight of the building. And that weight must be carried by the columns, the walls, and eventually it also ends up in the seismic forces on the building. So this whole focus on getting a thinner slab to work, it saves money on the columns and foundations, reduces the weight, reduces the material requirements for these elements. And if you're working in a seismic region, the seismic forces are based on the weight of the building. So if you can decrease the weight, you're automatically decreasing the seismic forces that you have to design to. And we'll find that we get pretty close to where seismic and wind in our particular area end up being just about equal. So we're getting a nice multi-hazard system going. There's actually been lead recognition for innovations in design, and post-tensioning is starting to show how that works. Reduction of concrete. This was actually a study done by Mr. Watry, I believe it was for PTI. 16% less concrete, sometimes more. Reduction in reinforcing steel. If you ever go out and look at a post-tension deck, there really isn't much steel in there. We've done a lot of decks where we had no bottom steel whatsoever in the slab. The frame cost comes down. The overall building weight goes down. You can lower the building height. We've actually had situations where we didn't want to block the view of an adjacent building, but in most cases, we're not lowering the building height, we're sticking an extra floor in there. And also faster construction. Analysis methods are really important now as well. You see wild designs that are coming up. The architects are getting very creative. And some of the old methods that we had, you go through your old concrete manuals and you use formulas, WL squared over 8, WL squared over 11. And these are all great, but the simpler methods are approximations. And because they're approximations, they have a conservatism built into them. So the conservative results can lead the designer to both choose a thicker slab that's necessary and put in more reinforcing in concrete that's necessary. So a lot of the industry is going to finite element analysis, where you're actually looking at the overall slab and really trying to determine its performance. I mean, we're not trying to cheat here. What we're trying to do is put the material where it's really needed. And the finite element analysis methods help you to do that. In an example, you don't want the building to be too flexible. You don't want to have too much deflection. So you can start to accurately look at what are your hot spots. How much deflection you're having. It's going to be a problem for the windows. Is it going to be a problem for the partitions, so you don't get too thin? And with post-tension, you can actually come back in there after the fact. You do your first run, and you can look at some of those hot spots and actually throw some extra PT in there if there's a problem, and lift them up a bit. Specialty products are coming out now. The construction industry has kind of been slow to evolve, but from a standpoint of slab technology, one of the big things that's been out now, actually developed in Canada, is stud reinforcing for punching shear. In the past, you'd either put drop panels or mini drop panels or thicken the entire slab, and now you can address it with punching shear reinforcing. It was discussed earlier, you're even using reinforcing that might be used for other things within the slab or the mat to handle that. It's a little bit hard to see, but off next to the rebar and between the PT, you can see the little studs. They're on little rails. Of course, column materials, what you want to look at, again, is you're selling floor area that's usable, so going to higher strength concrete, higher strength steels. Should always be using at least 75 KSI reinforcing steel in your columns. You're using less material, and you're creating better, more usable space. And that's done, again, just high-strength steel and also the highest strength concrete you can get. Unfortunately, in our area, we can't get very high-strength concrete. It just has to do with the aggregates that we have. And probably not a good idea for us to start shipping aggregates from Seattle over to Hawaii. It gets a little expensive. Design philosophy. We see a lot of engineers out there that feel they're pushing the limits if they design to the code. You're within 2% of the code allowable. You're going to have a failure. No, the code has safety factors, and we really don't have a right to add on to that indiscriminately, at least not without talking to the client. Sometimes you have to do it if you have serviceability issues, but to just throw extra safety factors in there just because you're wasting materials again. So in summary for this building, when compared to about 6 or 7 other high-rises in Honolulu, we found that we did end up saving a lot of rebar, we saved a lot of post-tensioning, and that efficiency could be used to actually build more buildings. So really looking at how can we get efficient, and through that we create sustainable design. I'm going to close with future projects because as engineers, we're always stuck in design analysis. We don't get to be too creative, but one of my clients who, oddly enough, sells motorcycles and cars is really big into sustainable design. His first dealership had photovoltaics on the roof. He's got natural ventilation, and he collects all the condensate water out of the AC system and uses that to wash off the motorcycles before he turns them over to the new owners. So he's looking at doing the new tower with photovoltaics on the roof, wind turbines up on the roof and other areas, actually extracting out some of the groundwater and using the condensate water and whatever rainwater he can get off the roof. So they want to incorporate all these great technologies, and at the same time we can help them to try and make an efficient structure. So in conclusion, the most effective contribution as a structural engineer that we can make is to work with the team, but be innovative in our design approach and really be material conscious. Try not to waste materials. So we have to start early with the architect, tweak things a little bit, help them see what we need and what we can incorporate into their vision and the owner's vision. And the successful completion of this effort requires appropriate analysis tools, quality control during construction. Thank you.